Okay, then the rules for addition and subtraction when using significant figures to determine the number of significant figures you should have in your answer are similar but not the same as they are for multiplication and division. In addition and subtraction, it's not the total number of significant figures we're concerned with, it's the number of decimal spaces. That is the number of digits after the decimal point. So the number of decimal spaces in the answer should be the same as the number of decimal spaces in the individual quantity that is least accurately known. Or in other words, the number that goes into the equation that has the fewest decimal spaces. Okay, so for example, if you take 17.85 centimeters and 3.973 centimeters, your calculator will tell you that the sum is 21.825 centimeters. The problem is that you don't actually know this number that accurately. It's implying that you know this number to the nearest thousandth of a centimeter, whereas you only knew this number to the nearest hundredth of a centimeter. So that's a problem. So this has 2 decimal spaces, and this has 3 decimal spaces, and we go with the less accurate number. So the answer should have 2 decimal spaces. So we're going to need to round it off. So we can keep the 8 and the 2, but the 5 has to go. So it's 21.8. Now, if the number you're dropping is 5 or greater, then the last digit you're keeping has to go up by 1. So that would be 3. 21.83 centimeters is the correct answer for that, to the correct number of significant figures. Or, sorry, correct number of, well, yeah, correct number of significant figures. Okay, so for addition and subtraction, it's pretty straightforward. Some books will tell you to line the numbers up in a column with the decimal points vertically on top of one another and round off to the the smallest number of columns to the right. I don't. That seems a lot more complicated than it really needs to be. Just add up the numbers and then go back and count up the number of digits after the decimal point in each one and round off your final answer so that it has the same number of decimal spaces as whichever of the individual numbers has the fewest decimal spaces. And you should be okay. All right, the next thing we really need to do is scientific notation. Scientific notation is used in science for, well, a couple of different reasons, really. One reason, obviously, is that it makes it easy to express really large or really small numbers in a compact and convenient form. And well, an example of that might be, for instance, if you have about, say, 21 pennies in your hand, which is a quantity you can easily hold in your hand, and they're the older pennies back when they really were made of copper all the way through, you might wonder how many atoms of copper are you holding in your hand? Well, the answer is about that many. That's a pretty big number. That's a number whose magnitude you can really only um, understand if you sit there and count all those zeros. There are 21 zeros after the 2, um, just so you don't have to sit there and count them. But yeah, I mean, you can obviously tell it's a really big number, but you can't really tell how big without counting all those zeros. That's tedious. It's hard to recognize at a glance. And that's why scientific notation is so useful, because we can write it in scientific notation as (6.02 times 10 to the 23rd power. Much more compact, much more easy to understand the magnitude of the number at a glance. 10 to the 23rd, you can understand that much more quickly than you can count all of those zeros. So it makes sense from that point of view. And another reason we can use scientific notation is to avoid confusion when dealing with significant figures. So suppose the answer to a calculation is 3,400, but you're only allowed to use 3 significant figures. How do you do it? How do you write that answer with only 3 significant figures? In the decimal form like this, you really can't, because with no decimal point at the end, it's ambiguous. So 3,400, written the way I've written it here, could be 2 or 3 or 4 significant figures. All we really know is that the 3 and the 4 are significant. Since there's no decimal point, these zeros at the end may or may not be significant. As I said, the tendency is to go with the smallest number of significant figures, if in doubt. So we would tend to favor 2 as the number of significant figures for that number. But it could be 3 or it could be 4. You don't really know. You could try putting a decimal point in, but if you do that, then it becomes 4 significant figures, because if you put a decimal point anywhere in that number, both of those zeros at the end will count. So you can't put a decimal point there and say, okay, only, because it's not a case where if you put a decimal point there between the 2 zeros, not just the numbers before the decimal point will count, but that 0 after the decimal point will count also. And it'll still be 4 significant figures, and 340.0 is not the same as 3,400. So there's no way to do it. There is no way to write that number in a decimal form and convey that it has 3 significant figures. But in scientific notation, you can take care of that by writing it as 3.40 times 10 to the third. 10 to the third is 1,000, so 3.40 times 1,000 is 3,400. But 3.40 clearly has 3 significant figures in it. The 3 and the 4 count as significant because there's a decimal point. The 0 at the end counts. That's 3 significant figures. So that number definitely has 3 significant figures. So it resolves the confusion in certain situations also. Scientific notation is a different way of writing the numbers. But it's not meant to change the value of the numbers. It's kind of important to keep that in mind, especially when converting from a decimal form to a scientific notation form or the other way around, because a lot of times, if you sort of keep in mind the fact that you're not changing the value of the quantity that's being expressed, it can help you with that transition by sort of reasoning it out. Say, if we make one part of the number bigger, we have to make the other part of the number smaller to balance things out. So you definitely don't want to change the value of the number. You're just expressing it in a different way. The proper form of scientific notation is a number between 1 and 10 times 10 raised to a whole number power. Okay, so those parts are both important. The first part of the number has to be between 1 and 10. It can't be 0.5. It can't be 16.8. It has to be between 1 and 10. And you can get it to be between 1 and 10 by moving the decimal point one way or the other, left or to the right. When you move the decimal point, though, you will change the power of 10 to compensate for the change in the number that's caused by moving the decimal point. And so that's what I mean by, like, if you change one part of the number, you have to change the other part to compensate. If you move the decimal point, you have to change the power of 10. Also, the power of 10 has to be a whole number. So if you have a number like 2.0 times 10 to the 3.5, that is not scientific notation, or not proper scientific notation, because it should be a whole number power. If you end up with fractional powers and you want to know what they are in proper scientific notation or something close to it, you can always enter them into your calculator. If you were presented with something like 10 to the 3.5, you can just take your calculator and put in 10 and raise it to the 3.5, and then hit equals, and there it is. Actually, that is a decimal form of the number. Your calculator actually can also be put into scientific mode. So let's see. For this type of calculator, it's the second function and then the DRG key. And flow is the regular decimal form of the numbers. And you can change it to scientific using the arrow keys and then hit enter. And that will actually change whatever is on the screen from the decimal form to the scientific notation form. So that number we just saw in scientific notation is 3.16227766 times 10 to the third. When dealing with these calculators, you have to be careful not to overlook the little exponent at the end. It's times 10 to this power. And a lot of times people don't notice that. On some types of calculators, the number is even smaller than it is on this one, so it's easy to overlook. So you have to be careful to look at that corner of the screen and make sure there's not something hiding there. And the times 10 on most calculators is really, really tiny. So be careful to look for that also. So this is the standard form, number between 1 and 10 times 10 raised to a whole number power. Just in case you're not that familiar with the concept, I'll start out by explaining what raising 10 to a power means. If the power is positive, then what that means is it's equivalent to writing 10 that many times, that is, the number of times in the power, and multiplying. Okay, so for example, 10 to the first power is just 10. 10 to the second power is 10 written down twice, and you multiply 10 times 10, which is 100. 10 to the third power is 10, 10, 10, and multiply them together, and you get 1,000, and so on. And it's also important to remember that any number to the 0 power is 1. That's a definition in math. So 10 to the 0 power is 1. Because that means that if you have something times 10 to the 0 power, you can just drop the 10 to the 0 power because it's just 1. And multiplying something by 1 makes no difference. If the power, on the other hand, is negative, then what you do is you write 1/10 that many times, and multiply. So if you have 10 to the minus 1, that's 1/10, or 0.1. If you have 10 to the minus 2, that's 1/10, and 1/10 multiplied together, that's 1/100th, or 0.01. If you have 10 to the minus 3, that's 1/10, 1/10, 1/10 multiplied together. In other words, that's 1/1000th, or 0.001. And of course, it's still the case that 10 to the 0 is equal to 1. Converting from decimal to scientific notation is an important thing to be able to do. So converting from decimal form to scientific notation. What you want to do is move the decimal point in the given number until that number is between 1 and 10. You can move the decimal point either way to do that. And when we say between 1 and 10, that's kind of a shorthand way of saying it. The 1 is inclusive, meaning that the number could end up just being 1. That's okay. But it can't actually be 10. It has to be less than 10. 9.99999, on to infinity is perfectly okay. But 10 actually wouldn't be. If you get 10 then what you're going to want to do is move the decimal place one more place and end up with 1, and then change the exponent, or the power of 10. And then you add times 10, and the 10 should be raised to the power that's equal to the number of spaces the decimal point moved. Okay, and then the question is, of course, whether that power should be positive or negative. And a lot of books will explain it, well, if you move the decimal point to the right, then the power, then the number should be positive. And if you move it to the left, then it should be negative. And that's easy to get mixed up. So I usually prefer to just reason it out. If you think about it, you're not trying to change the value of the number. So if moving the decimal point made the number smaller, the power should be positive. Okay. So essentially, if moving the decimal point makes the number smaller, you're making the exponent bigger to compensate. One part of the number is smaller, the other part of the number has to get bigger, so things will even out and the value will remain the same. And it works the other way around too. If moving the decimal point makes the number bigger, then the exponent should be negative. And an example of that, say, would be the number 96,485. If we start out like this, we can think of this as being 96,485 times 10 to the 0 power, because like I said, anything to the 0 power is 1, and you can multiply anything by 1 without changing its value. So you could take any number you see and consider it to be times 10 to the 0. So 96,485 is the same as 96,485 times 10 to the 0. If you move this decimal point to make the first part of the number between 1 and 10, you have to move the decimal point to the left. Because obviously, if you move it to the right, you're making the number bigger. It would be 964,850. You're getting further away from that range of 1 to 10. So we move the decimal point to the left, 1, 2, 3, 4 spaces, and we get 9.6485. That is between 1 and 10. It's close to 10, but it's less than 10, so it's between 1 and 10. And that'll be times 10. And the exponent will be the number of places we moved the decimal point. That's 1, 2, 3, 4. And because moving the decimal point made the number smaller, 9.6485 is definitely smaller than 96,485. So we made the first part of the number smaller, so we have to make the second part, the exponent, bigger to compensate. And plus 4 is definitely bigger than 0. So these two numbers are equivalent to each other. And you can even try it because to check, because 9.6485 times 10 times 10 times 10 times 10 should be 96,485. So this is the scientific notation. This is what it means, and this is what it's equal to. Okay, we can do it with smaller numbers also. 0.08206. We can consider that to be itself times 10 to the 0, because 10 to the 0 is 1 and it doesn't change the value. And then we have to move the decimal point so that the number is between 1 and 10. If we move it one place to the right, we get 0.8206. That's not between 1 and 10, but we're getting close. It's almost 1. We move it one more space, we get 8.206. That is between 1 and 10. Okay, so 8.206 times 10 raised to a power. The power should be the number of spaces we had to move the decimal point, which is 2. But in this case, moving the decimal point made the number bigger. 8.206 is definitely bigger than 0.08206. So to compensate for making the first part of the number bigger, we have to make the exponent smaller. So this is going to be -2, which is less than 0. Okay, so 8.206 times 10 to the minus 2. And that's equivalent to 8.206 times 1/10 times 1/10. And if you actually try that on your calculator, you will get 0.08206. And so there you go. Okay, that actually brings us to the end of this segment. And that's the end for this second lecture. So I'm going to have to pick up there in class when we meet again on Monday or Wednesday next week. Okay, and so I'll make a note there and we'll pick up there next time. See you then.